Swayam Prabha. Digital India. Educated India.
Okay, all right. So kind of refresh what I said before the break. We are going to start talking about system path interactions and what happens to my probability distributions, probability densities when I have a path interacting with my system. So if I go back into time evolution of an isolated quantum mechanical system, time evolution fundamentally laws of quantum mechanics is time invariant or invariant under time reversal, which means if I have an initial state, I go in time in positive time direction, I reach a final state. In principle, if I travel back in time, I should come back to life. Right? That's the basis. You can kind of see what I've seen so far. But this is really true in isolated systems. In reality, no system is isolated. It's always an open quantum system. It's interacting with a path. So we should, in that case, this reversibility sort of is violated. So you have irreversible relaxation coming because of this path interaction, which, by the way, is the focus of nonlinear spectroscopy. We want to be able to capture that irreversible relaxation, decoherence processes, which gives us a lot of insight, mechanistic insight into the material physics. So how do we define a path? So you should be able to define a path. How do we define a path? Which it interacts. So one way of dealing with a path is by defining it as a closely packed manifold of energy states or a continuum of states. So we kind of define the path as closely packed manifold of these states or some broad distribution of energy states that are existing in close contact with your primary quantum system of interest, which we call, for the sake of simplicity, our system. Our system is some state I have some slightly changing the notation here. Sorry for that. I have some my quantum state, which I could maybe drive this using some potential, time morphic potential. Now what I do is I define a path here as a manifold of energy states. Let's call them n. And you can have relaxation of my quantum state into these closely packed manifold of energy states or continuum of states, which we call as the path. Okay, such kind of examples of continuum. It could be, for example, some kind of bond potentials in which energy exceeds the binding energy. For example, what is possible when you have photodissociation of a molecule? You just open up coupling into a continuum of possible modes in the system. Or another very widely used example are the lattice vibrations of a crystal. Okay, they are like a continuum of states available, huge bath of phonons available to scatter your quantum state, the electron, for example, in an excited state. Or in a semiconductor or even in metals, you have actually a continuum of electronic excited states, which form a broad continuum, and that could be also your path. So your bath can come in different flavors, different kinds, so on and so forth. But the essence is, the most general case, I could define my bath to be some sort of continuum. Fair enough? Fair enough? Okay, so if I want to now estimate what I want, I'm kind of interested now is to understand what is the probability of my state, my system, which is at state K, sort of decaying into this continuum of states. I'm getting lost, which is irreversible, right? It's kind of lost channel in my system, of my system. And because of that presence of that channel for my system to go into, what happens to the probability of absorption if this excited state decays? Okay, that's the question that we are trying to ask ourselves. Now, for that, we need to kind of define kind of mathematical framework which defines that transition from my state into the bath. And typically, it's some kind of first order kinetics behavior. And first order kinetics, you should be able to write down the probability decay of that state into the continuum of states to be some exponential function. It's not unreasonable to think about it that way. Some exponential decay function. So my quantum state can decay exponentially and irreversibly into this. Now we are asking us a question, when I have this kind of pathway, what happens to my probability of absorption between these? So I have this decaying into this in this particular way in exponential fashion. What happens to my absorption? That's what I'm asking. Again, going back, we need to work around the time evolution of the relative amplitudes. For now, I'm going to assume for the sake of discussion, my BL of T to be almost 1. What does this mean? My BL of T, L is my ground state here, the lower one state, is almost 1. Most of the system is in the ground state, which is kind of consistent with our earlier assumption that we are in the weak perturbation. Now in this case, now I can write down my equation of motion for BK cool. Now independently, I can show, I'm not going to derive this. There are extensive notes with me. I'm not going to show you this, but it can be shown that in a case where you have irreversible relaxation, and you can use Fermi's golden rule for the scattering probability of quantum state going from your K state and scattering into the continuum of states, you can show for an irreversible relaxation, my BK of T is some exponential of over 2 minus I delta K over H cross. Now, what are these terms? So, your W and K is basically from Fermi's golden rule, the transition rate from the Fermi's golden rule. So, it relates to wave function overlap and the density of states in the continuum, which overlaps energetically with your quantum state, so on and so forth, right? And delta EK here is some kind of correction to the energy, second order perturbation theory. You can kind of say, okay, because of the presence of my continuum and the scattering, I'll have a slight renormalization of the energy of my state. Okay, and that's, you can show this And again, as I kind of predicted earlier, this is an exponentially decaying function. Okay, so this is an assumption and a consideration based on physical intuition that I wrote it down, but it can be explicitly shown to be this. Of course, pk is square of pk. I'm not deriving this because it will take another 1 hour to kind of properly derive this, which we're not going to do. I'll leave it in the notes. For the sake of convenience, we'll just say my delta ek is 0, which means that presence of this continuum, presence of this bath is not changing much the energy of my state, which is a reasonable thing to assume, especially when you have, for example, your system interacting with phonons. Presence of these phonons is not going to strongly denormalize your energy state unless, of course, you are in what we call as polaronic regime, which is something that we're not talking about. There again, like if I bring two quantum systems together, I always have weak coupling regime, strong coupling regime. The physics of strong coupling regime is completely different. It's much easier to work in the weak coupling regime, and weak coupling regime, of course, works for majority of the cases. When it works, we use it, right? But of course, there are some cases it doesn't work, and that's where the active research happens, and that's where we want to do more careful experiments to identify, which kind of regime we are in to kind of begin. So, assuming that the bath interactions are related to the weak coupling regime, you can kind of say my delta ek, my correction to my quantum state energy, is 0. Okay, now making these considerations, so assuming the specific form for bk, which is basically telling you the relaxation rate or relaxation amplitude because of scattering into the continuum, now I can write my time evolution of bk in the presence of an electromagnetic field, of course, is minus I over h cross e to the power I omega kl t e kl of t minus w and k is the transition probability. Now we know we have just derived v of t. V of t is minus I e naught mu kl sine omega t mu dot minus mu dot t, and we just derived that. That's a form for electromagnetic wave. If I substitute that, then d over dt of bk is minus I over h cross e to the power I omega klt sine omega t b kl minus w and k, just putting this dash to kind of represent that the transition probability is not frequency. The w and k is, so this term that you're getting here is a dissipation term, if you think about it. Like a dissipation term because of scattering into the continuum. And that is determined by the scattering rate or transition probability. Okay, which is related to system bath coupling at the end of the day. So I can expand this out a bit more using the exponential representations. L plus omega t minus e to the power I omega kl minus omega t mu kl minus w and k to k t. Now it so happens, of course, this is a kind of reasonably standard differential equation of the form y dot plus ay equals b e to the power minus alpha t. That is the case my y of t is given by a e to the power minus alpha t plus b e to the power of I alpha t over a plus I alpha. If you make appropriate substitution, you'll get an expression for bk, which again is in my notes. I can again make rotating wave approximation, so drop out my high frequency oscillations because they're going pretty fast, and also make an assumption of long time limit, which is basically in essence that I'm not looking at very fast oscillations. Then I will get a pretty neat looking expression for bk. I mean, let's look at the expression. It looks elegant, I would say. E naught ukl cross over I omega kl minus omega t starts to get into a form which we like. Okay, that's your bk of t. Don't confuse between omegas and w. Unfortunately, when I write, they look almost identical, but they're not. But of course, we are not interested, we don't care about bk's. What do we care about? The square of the amplitude, the probability to, so what we are caring is the total probability to transition to k, driven by the electromagnetic field. If I take that pk, which is pk square, is E naught square mu kl square, square of the transition dipole moment, 4h cross square, 1 over omega kl minus omega square plus w nk equal 4. This is a pretty neat looking expression. Again, something that tells us is that a transition probability driven by an electromagnetic field is a Lorentzian function again. It's again a Lorentzian function. Again a Lorentzian function. Again, I can get a Lorentzian, right? Doesn't matter. My full width half maximum now, the full width half maximum now is given by W and K. And that is significant. That is significant. That is significant. So I'm looking at transition probability with my electromagnetic field. It's like you're measuring an absorption spectrum, right? You're measuring an absorption spectrum. The line width of that transition now, in the presence of the bath, the full width of maximum is related to the scattering of my system into the bath. So simply by measuring my absorption line width, I'm able to access the transition probability for my system to scatter into the bath, the coupling of my system into the bath. Again, I'll kind of refresh your memory. This is my L, this is my K, and then I have some scattering into some continuum of states. And this scattering is given by my W and K. Right? You're driving the system here, resonant with the transition of my quantum state, and I'm measuring absorption spectrum. But the line width now gives me information of something completely intrinsic to the material. That is the strength of spectroscopy. Now I can start talking about understanding open quantum dynamics of the system by using my light as a probe. So the full width of maximum gives me basically the relaxation rate from my quantum state K into the continuum N, my bath. And another important thing, here if you look at it carefully, the line width is completely related to the system. It has no relation to the perturbation that is driving it, the electromagnetic field that's driving it in this limit. So when you have strong, relatively non-negligible system path interactions, then the line width that you measure in absorption spectrum is exclusively coming from the system. It has nothing to do with the field that is driving it. So you're really in this regime where with electromagnetic field, you're only seeing, you're not perturbing the system. You're not perturbing, you're of course perturbing the system, but you're not changing anything in the system. You're accessing a parameter which is intrinsic to the material. That's a very important thing, firstly. And secondly, you already kind of know the line width is related to this coherence in the system. And if I have more and more path interactions, stronger transition probability, my line width will increase, which means my coherence is getting destroyed. The system path interactions fundamentally destroy coherence. And that's the reality of nature. No system is closed. What is it? How much is that effect can change. Some systems you can preserve coherence for a substantially long period of time. Some cases, everything is dead within hundreds of femtoseconds. And this is exactly the problem that we are interested in. Okay. So far, again, we have treated everything using my amplitudes of the wave function. Of course, we wrote everything in interaction picture, but nevertheless, we are still working with amplitudes. So let's make, and it works reasonably well. This is linear response function. It works okay. But once you go to nonlinear response function, it becomes cumbersome. So we have to again go back to the density matrix. I'm not going to give you all the details at this point in time already. I'm going to expand this in the next class. But nevertheless, I want to give you a preview of what's going to happen. So we'll go back to our density matrix. Remember our friend, density matrix? Density matrix is indeed our friend. Okay. Which is defined as projection operator. And we also know the equation of motion of my density matrix. Very elegant. In fact, if I write this interaction picture, this Hamiltonian will simply be the interaction, the potential in the interaction picture, which is transformed as the basis of the unperturbed Hamiltonian. We call those things. But this equation here, which we kind of spoke about in the last class, strictly for open quantum systems, for closed quantum systems, for open quantum systems, or open quantum systems, which are basically with half system path interactions. We may want to explore it in this framework. Where you have an explicit dissipation error. This is coming from system path interaction. Hopefully, next time we'll talk about it. There are some operators called Lindblad operators, which are really helpful in this case. Always remember, we are going to operate in the rotating wave approximation. Basically, what that means is drop, fast, oscillating terms such as I omega plus omega naught e, but we are happy to keep sort of energy conserving terms like e to the power I omega minus omega naught. Very important. And remember, rotating wave approximation is valid when you're driving close to resonance. We have seen that already in this class. That's an important criterion. Another thing which is kind of implicitly there is that the coupling is much smaller than the frequencies itself, weak coupling regime. We are also assuming having the slowly varying envelope. We're not going very fast with electromagnetic field kind of getting the envelope. So the physical picture of rotating wave approximation, you're operating close to resonance, the weak coupling regime, and you're dropping all the high frequency components, so you're sort of using the slowly varying envelope. The physical picture is that you're transforming to a frame where the system appears to be sort of time independent, at least close to resonance. The Hamiltonian looks kind of close to time independent. It's of course not time independent, but close to time independent. That's the whole point. Okay. So what we will do in the next class is sort of develop this formalism a bit more. So kind of speak about system path interactions now in the language of density matrices. Specifically, we will develop what are called optical lock equations, which are basically these equations of motion. And in the next class, I would suggest we come with laptops and already install this package called Qtip. It's a Python package for quantum optics, Qtip. Okay, and let's see if we can make some exercises out of it in the class and also beyond. So Qtip helps you to kind of simulate or define first a density matrix and simulate some quantum dynamics. I kind of joke with some of my collaborators is that advent of Qtip enabled me to work without a theory person. I'm joking. I didn't mean that way, but at least we can, as an experimentalist, as a dumb experimentalist, I can still try to do some bit of theory, which is kind of spectacular. So we can kind of go over the Qtip a bit of basic, and we can kind of take a simple two-level system with some dissipation term, and we'll try to write out and see if you can simulate something on it in the next class. Okay, any other questions? So the takeaway from this is two things. The interaction is mu dot E. Okay. Tonight I'll come and wake you up and ask you this. No, joking. Careful numbers. More than mu dot E, there should be A dot P, that is a precursor for mu dot E. So that's first thing. The second thing to remember is that the line width of my transitions gives you access to system path interactions. That is extremely powerful. Extremely powerful.